hyper way too distracting. There we go. I'll bring him after the AP test. How about that?
So this is how you're going to solve it?
Huh? Yeah, right.
Put that in your bag or it's going to fly away in the wind outside. Oh, yeah. Seriously, it's really bad.
It is. All right, continuity. So for continuity, it says, if you haven't been here earlier, at the very beginning we talked about some books that I think are probably pretty good quality AP review books if you don't have one already and you would like to get one. The 3 books I mentioned were the Princeton Review, which is this one here. It's a pretty thick book. This has the AP Calculus AB and BC exams in it. It has like 6 practice tests in it, and it has a lot of explanation as far as what the sections are, but like for each section, like there's maybe 5 or 6 pages on similarity. So you can read really quickly about what similarity is, and then it gives you like 30 examples to do, and then it says go back and check your answers to make sure you got it right. And it will explain what the answers are, but it's just very cut and dry, kind of like that. It doesn't have much conversation piece to it. The book that we're working out of here in this PowerPoint is called Peterson's review book. It's Peterson's AP Calculus review book. I like it because it's more of like a dialogue. Like he has like, it's not just such a dry read. Like he's got some stories to it and he's got some examples to illustrate things. So I think that it makes it easier to study when you're able to read things that are more like, I can read this. I'm not super bored when I'm reading this. And he does a good job of integrating his explanations and solutions into the actual text that you're reading through rather than having to like flip back to a different page and read a bunch of solutions there. So that's why I like him as well. So Princeton Review, Peterson's, and then the third one I've heard of that's good is called Barron's. I haven't had a chance to look at it, but I've heard that it's good, yeah. So, for continuity, it says, I've had some bad experience in the movies, da-da-da. Again, that's like fun stuff that Peterson likes to put in there. We can obviously skip ahead to that. So, continuity is different than limits how? Good. So remember with limits, we didn't care if it equaled a certain value as long as it was going toward a certain value. If it didn't specify left or right-hand limit, the left and right-hand limits had to be equal. So in order for the limit to exist, the left and right-hand had to be equal to each other. With continuity, it actually does have to equal the point that it says that it's going to in order for it to be continuous. So you can't have any holes, you can't have any jumps, you can't have any gaps. So up here it says mathematically a function f of x is said to be continuous at all x equals a if these 3 things are true. So the limit has to exist, meaning the left and right-hand limits are equal to each other. F of a has to exist, so you actually have to have whatever f of a is equal something. And then the limit that you got for number 1 has to actually equal what f of a equals. So you can't have anything not equaling there. So those are the 3 conditions. Remember, these are the types of discontinuity we learned about. So this would be a hole or a removable discontinuity. Yeah. This one over here is the jump discontinuity. This one's the hole, and this one's the infinite unbounded discontinuity. So these are the 3 examples of things that would make it not continuous or discontinuous. But as long as those 3 things don't happen, then you should be good at any point. So, example 4, on what intervals is this function continuous? Ideas? Are you trying to leave?
Not negative. Can I make a little pass or something?
Of course. You just can interrupt me. And why do you say negative 3?
Because it's undefined at negative 3 at the bottom.
Good, it's undefined at negative 3. So if you plugged in negative 3 into the bottom of this, it would actually be undefined. The reason we know that is actually because if you plug in negative 3 to the top as well, what do you get when you plug in negative 3 up here? 27 minus 9 minus 15 plus, what is that? 51.
0.
It is 0 actually, yeah. So if you factored out an x plus 3, you'd actually be able to factor it out and you'd realize there was a hole. So if you put this into your graphing calculator, it would look like it was continuous because graphing calculators don't show holes very well. So it's up to you to know that it would be discontinuous at x equals negative 3 because it would make the bottom of the function equal to 0. So there would be a hole at x equals negative 3. So good. This one is continuous from negative infinity to negative 3 and then from negative 3 to infinity. Yeah, union. I always forget that part.
Is that important?
The union?
Yeah.
Yes and no. I don't think they would take off too many points. I mean, is it the proper notation? Yes, but could they probably figure out what you're talking about without that? Yes. I don't think they would. Yeah. Oh, didn't say anything. All right, example 5, we ready for that one?
Yes.
Okay, here's example 5. Try this one. All right. So first of all, how do you know where the discontinuities are?
You have to factor it.
Factor the bottom and set it equal to 0. So x plus 2 over x plus 2x minus 2. All right. So at where are the two discontinuities then? We have one at x equals negative 2 and we have one at x equals positive 2. What type is each one of these discontinuities? I hear negative 2 is a whole. Who can tell me why negative 2 is a whole? Good. Remember when you have common factors on top and bottom, you can always cancel common factors. And if that is able to happen, that means that there would be a whole at that place. So there's a whole at x plus 2, meaning that this one here is a whole. So this is a, we call this a removable discontinuity. A whole is like layman's terms. But on the AP test, you might see it as a whole. You might see it as a removable discontinuity. And then what about x equals positive 2? What's that one? It can't cancel, so it's not a whole. Say it again. What are the other types of discontinuities besides the removable whole? There's a jump. Is this a jump? It's not a jump. You actually won't get a jump unless you have a piecewise function, because there's no easy way to make a jump other than a piecewise function. That would be something for differentiability. It's unbounded, yeah. Whenever you have something that makes it discontinuous, or I should say undefined, like x equals 2 for this example, but it can't cancel with anything on top, that's an unbounded. Because remember, that's where the vertical asymptotes are. So on the bottom of the fraction, wherever it equals 0, if it's a whole, it'll cancel. If it doesn't cancel, that means it's a vertical asymptote. So this is a vertical asymptote, which means it's an unbounded discontinuity. So this graph actually looks something like this. So at negative 2, there's a hole right here, and at positive 2, there's a vertical asymptote, and it looks something like this. I mean, not a perfect picture, but you get the point. So there's a hole and asymptote. All right, we good on that one? All right, try number 6. It says, find the value of k that makes f of x continuous. All right.
Never mind, he's probably right.
Okay. So, for example 6, this is a piecewise function. So what do you know is the one thing we have to look for to make sure that these are continuous? That it's defined where?
In the first equation.
What about at 2?
It's a break.
It's a breaking point, right? So the fact that it's a breaking point means that we have to make sure that what happened? Good. We have to make sure that the limit equals the same thing from the left and right hand side so that we can make sure that there are no jumps. Because remember, the piecewise function is the time we will most often get a jump if you don't make those two limits equal each other. So for the first one, what does x equal, or I should say when x equals 2, what does that first equation equal? Good, the square root of 11. So that would be the square root of 11, which means we need to make sure that this bottom equation, when we plug in 2 plus k equals the square root of 11 at x equals 2. So we plug in 2 squared, which is 4, minus 2 plus k equals the square root of 11. So we have k equals the square root of 11 minus 2. And then in the calculator, that is about equal to 1.317. She says, yeah. Oh, you actually figured it out. I just thought you just were agreeing with me.
Oh, no, I actually figured it out.
Oh, good.
Doubting me?
No, I thought you were just humoring me. All right, so that's about equal to 1.317. If this was a calculator problem, you would be expected to come up with a decimal. If this was a non-calculator problem, you would just be expected to leave it as the square root of 11 minus 2. So that would be perfectly fine for an answer. All right, good. Ready? We're going to do some examples you guys are going to work on your own. Oh, that's right. I forgot. I just like to get powering through. All right, so for that first one, it says explain why the function is discontinuous and determine if the discontinuity is removable or non-removable. So it's discontinuous at x equals 3 because there's a jump in the graph. The limit as it approaches from the left is 3. The limit as it approaches from the right is only 2, excuse me. So this is a non-removable discontinuity because you can't just easily fix it. It's not just like a hole you can fill in. So this is non-removable. If you factor the bottom, you get 3x plus 1, x minus 2. So it's discontinuous at x equals negative 1/3 and at x equals positive 2. Which of these is a hole? It's a hole at the one that gets repeated, remember? So it's a hole at negative 1/3 here and here. So that's a hole, which means that this one is a removable discontinuity. So whenever you have a hole, you can always, it's a removable one. So this is removable. And it's because it's a hole, because you have the same factor on top and bottom. And then x minus 2 is not a hole, it's actually a vertical asymptote. And because it's a vertical asymptote, that means it's unbounded, because it goes to infinity. Good, and it's not removable because it's not just something simple you can replace. So this is non-removable. If there's nothing on the top that will cancel with it, but it's undefined on the bottom of a fraction, automatically it's a vertical asymptote. So the three cases of things that would make it discontinuous, the first one is a hole. That happens when you have something that's the same on top and bottom, or if you have a piecewise function like we did. Remember that piecewise function, it was defined at this function everywhere except where x equals 4, and then all of a sudden at x equals 4 it was 0. That would be a hole in the graph. So a piecewise function can create a hole like that, or a function like this can create a hole where the same factor appears on top and bottom and you can cancel them out. So those are the two places you'll see a hole. To see a vertical asymptote, it will appear in something like this, where you have a factor on the bottom of the fraction that doesn't appear on the top, and so that's a vertical asymptote automatically. And then a jump discontinuity can appear in a piecewise function when you have the left hand and right hand limits at some value not equaling each other. And that's where you'll see a jump. And then for the third one, it's discontinuous at where? At x minus 5. But if you notice, the top is actually x minus 5 squared. So the square root of x minus 5 squared is just x minus 5 over x minus 5. So that's 1 over 1, yeah. So there's a hole. So it's still discontinuous at x equals 5. There's a hole. So it's a removable discontinuity. So those are the three cases where you'll get a removable discontinuity or a hole or an unbounded graph like that. I lied though. This one's not removable because of this. Square root of x minus 5 squared is plus or minus x minus 5. So I lied, sorry, that's not a hole. When you get plus or minus x minus 5, it depends if it's the not positive or negative version. So it's actually, it looks like an absolute value function like this. Oh, not there though. It looks more like that actually. So yeah, it's a jump actually, which is a non-removable. So to clarify that, because I don't want you guys to get confused on the test about that. We know that this one is a jump discontinuity and not a hole, even though it equaled the 1 over 1 kind of thing. Because when we took the square root of x minus 5 squared, it did equal x minus 5, but it equaled plus or minus version. So whenever you have that positive, negative, you have to see where it would be greater than 0 and where it would be less than 0. So the break is at x equals 5. So that's why it looks like this. Keep that in mind. All right, these next ones, you shouldn't use a calculator for either. Don't actually worry about number 4, because it says describe the continuity of the 15 functions you were told to memorize. I never told you to memorize any 15 functions, so don't worry about that. Number 5 says draw the graph of a function f of x that satisfies each of the following conditions, then describe the continuity of the function. So try drawing that graph for 5. And then try number 6 as well. If you want to go back through and just verify that all of these things we just said were correct, the limit as it's approaching positive 2 equals negative 1, that's true. The limit as it's approaching 0 from the positive side goes to negative infinity, that's true. The limit as it's approaching 0 from the negative side goes to positive infinity, that's true. F of 2 equals 4, that's true. F of negative 1 and 3 equals 0, that's true. And F increases on the entire domain, that's also true. So we got this down pat. Does your guys' look something like this one? It doesn't have to look exactly like it, but it should look something like it. Did you have a chance to work on number 6 yet? 6 is a lot like number 1. Find the value of k that makes p continuous if p of x equals that. So on the bottom function, I need to figure out what would make, or what that equals when x equals 4, because remember that 4 is that breaking point. So I have to make sure that those two sides are equal to each other at the breaking point. So what do you get when you plug 4 into the bottom equation?
You get
You get what?
5.
5, okay. So negative 16 plus 44 minus 23 equals 5, which means that that needs to equal the negative absolute value of x minus 2 plus k when x equals 4. So if I plug in 4 for x, I get 4 minus 2. The absolute value of 4 minus 2 is 2. So that's negative 2 plus k equals 5. So k equals 7. So remember number 6 and number 1, the ones that look like this where you have to make them continuous, those ones we keep seeing a lot actually in class. I remember we saw them a lot in class, we saw them on our tests, we're seeing them here in this review book, so you could probably almost guarantee that there's going to be like one like that on the AP test, just to keep in mind. And they're not too bad, so hopefully that's okay. All right, can we move on? C.
The one where you draw the graph, will that be like a short answer question?
Yeah, it would have to be a free response. I don't think that they would, it's almost too easy to have them give you the graph because it would be pretty easy to figure out which one it is from the graph. So I would think that if it was going to be on the AP test, it would probably be, it might be a multiple choice, but I would think free response. All right, it says you may use your calculator for all of these problems. So you can do these on a calculator. Make sure you have your calculator with you. If you don't, you can come grab one. It says for each of the following functions and intervals, determine if the extreme value theorem applies and find the maximum and minimum of the function if possible. So do you guys remember what the extreme value theorem is? No. Do you guys have your notes from last semester? No. All right, then let's get it up here on the board. I'll try and take a picture of it out of the book. Let's see what page it's on. Oh my gosh, I hate this stupid book. They're like, the extreme value theorem is on page 886. Well, guess what? My book only goes up to page 700. Let's try this one.
Oh, is it an extreme value?
Here we go. I found it.
I thought it had the tongue.
It's not gonna work. Okay, so I'm gonna put it up here and then I'll take it down. So you're only gonna be able to see it for a short amount of time. All right, it says if f is continuous on a closed interval from a to b, then f has both a minimum and a maximum on the interval. Not too hard, right? So here's what that means, and see if you can recall with me back to when we learned about this. As long as there are no jumps, gaps, or unbounded places in the interval, and it's a closed interval, so including the endpoints, f has both a minimum and a maximum on the interval. It could be in the middle of the interval somewhere, or it could be one of the endpoints. So do you remember how we had to test like all the mins and maxes to find if there were some in the interval, but then we also had to test the endpoints to see if they were the high or low points? So that's what this is saying, is that there is some min and there is some max, and it could be at one of the endpoints, but test all of them. You can use a calculator, so you can see a picture of it, or you can use your table or whatever. So for each of the following functions and intervals, determine if the extreme value theorem applies. So first of all, determine if it's a closed interval. That's all that you have to determine. Is it continuous and on the closed interval that it's saying? And then if so, find the minimum and maximum of the function. So I'll give you guys a few minutes to try these ones. So that's obviously you're testing your knowledge of whether or not you know the extreme value theorem. So extreme value theorem does not apply. And that's because tangent of x is not continuous on this interval right here. Let's look at number 2 together just because it's a lot to look at and a lot to take in. We're looking from negative pi to negative pi over 4. So if I can actually draw that, here's negative pi going backwards, and the negative pi over 4 is right here. So we're actually looking in this interval here, going in that direction. And sine, is sine ever not continuous? Sine is oscillating, but it's always continuous, right? Yeah. Sine and cosine are always continuous, so that one won't give any issues. But what about cosecant? When is cosecant not continuous? Cosecant is 1 over cosine. No, 1 over sine. Thank you. Cosecant is 1 over sine. And so we need to know when sine is equal to 0. Where is sine equal to 0? Sine is y, yeah. At 0 and negative pi, right? So it would be, cosecant would be undefined, and that's okay actually, because this is when it's greater than negative pi over 2, so this is the piece that we're looking at for cosecant. And then when sine is between less than negative pi over 2, so this is the piece we're looking at for sine. So since this piece here is the only piece on our interval that cosecant is undefined, then we're okay. So the extreme value theorem does apply because there are no places on our interval where this function is undefined for the bounds that it has set forth. So then you have to find the minimum and maximum of the function. If possible, of course. And you're allowed to use a calculator. Keep that in mind. So the max is at x equals 0. No, x equals pi, negative pi. And it's a maximum of y equals 0. We saw that one from our Desmos graph. And because it decreases for the remainder of the interval, we get that minimum over at negative pi over 4. And we saw that in our graphing calculator. X equals negative pi over 4 of y equals, I think the decimal was negative 1.414 or something. So we could get that in a graphing calculator. You just have to be able to verify which pieces of the graph you're supposed to be looking at. All right, I know that was a little bit of a confusing one. So let's move on before we kill ourselves. All right, number 3. Put that in your graphing calculator. I'll put it in mine too. It is exponential. Better than trigonometric, right?
Yes.
So e to the x minus x cubed. And change your window back to like normal window settings so we don't have craziness anymore. And then actually you can look at it from -2 to 4, so you can change your window from -2 to 4.
For the X. We'll do a Y.
Say it again. For the X, this window here, the -2 to 4 that's given here, these are always X windows.
And the Y can just be.
The Y can be whatever it needs to be, yeah. You can just look at the function, as long as you can see the whole thing. So you guys have that x, e to the x minus x cubed? I'm going to show you on my graphing calculator just so you guys can see it on mine. Does yours look like this? So is it continuous everywhere in its domain? Yes, because x cubed is continuous everywhere and e to the x is continuous everywhere. So it is continuous everywhere in its domain. There's no holes, there's no jumps, there's no gaps, there's no unbounded places. So the extreme value theorem does apply. And the next question is, can you find the maximums and minimums? And remember that if it doesn't say absolute max and min, that it means like all of them. So can you at least see where they would be? Do you know how to make your calculator find them for you? We've done it before, so if you forgot, that's okay. We can go through it, but here we go. So if you, here, I'll wait. Is everybody, I just want to make sure we're all on the same track. That's weird. The solution to this in the book says that the extreme value theorem does not apply. Say it again?
If you look at the very bottom right corner.
But isn't that just because I'm cut off though?
Yeah, it just got cut off because you have to wait for them.
If I go down to negative, or sorry, positive, if I go down to -11,
It's fine.
it shows it there. I'm wondering if it's because, let me go back and look at this. Should be good. Oh. I guess e to the 0 doesn't work out. That's not true. Shh, quiet yourself. All of these should be good, right? There's nothing you can plug in there that would make it undefined. I don't know why they say that it wouldn't work. It says the extreme value theorem will not apply, but the function still has a maximum and a minimum. Extreme value theorem says if f is continuous on a closed interval, this function is continuous on that closed interval. That's weird. Okay, I don't know why it says that the extreme value theorem will not apply. I'm pretty sure it does, because it is definitely continuous on this closed interval. There's no holes or gaps anywhere. It wouldn't give me any issues. But that only applies when you're looking at differentiability, not when we're looking at continuity. So I'm not sure why, but you can still figure out mins and maxes. So let me teach you how to do that in your calculator. All right, so you go over here. See how there's a minimum right here, but we don't know where it is yet? So let me zoom in for you guys so you guys can see. If you push second, calc, and then go to minimum, it's under trace. Second calc, go to minimum. And then if you scroll, it says a left bound, so just find a point that's on the left of that minimum right there and push enter. Underneath trace, right next to graph. So go second calc, push minimum, and then it says left bound. So if I'm pointing right here with my finger to the minimum, you need to find a point to the left of that. So you just use the little cursor to scroll over until you find a point that's to the left of that. And then push enter. Then it says right bound. So then if I'm holding my finger on the minimum, I'm going to make my cursor go over here until I'm on the right hand side of that minimum. And I'm going to push enter. And then it says guess. So I'm going to go back to the middle again where I think the minimum is, and then I'm going to push enter one more time, and it's going to find the minimum for me in that interval somewhere. So I gave it a left bound, I gave it a right bound, I guessed where it was, and it found the minimum. You didn't know how to do that?
I didn't know how to do that because whenever it would ask me left and right hand, I would just press enter the entire time.
There you go. So it tells me my minimum is located at x equals negative 4.59, and it has a minimum of negative 7.29. And then you do the same thing for the maximum over here. So again, you can go to second, calc, maximum. And you can do a left bound, and you go to the right-hand side of the maximum, you push enter again to do a right bound, and then you go back to the maximum and you take a guess at where it is and you push enter for guess, and it will find the maximum at 0.910 at a value of 1.731. So good, I'm glad that a few of you guys didn't know how to do that so that you know now. That's really crucial for the AP test because if you're on a calculator section and you're allowed to use your calculator, it says find the minimum and maximum of this. How easy is it using this calculator? Super easy. This thing also does a bunch of other things for you, like if you push second calc, the value is the same as like the trace button, so that doesn't really help that much. If you want to find a zero, like if you need to find the zero, for example, if it says, if it gives you like a first derivative function and it says find where the original function has turning points, you could plug that first derivative function into your graphing calculator and then use it to find the zeros, and that's where the original function has its turning points. So that could help. Use minimum, maximum. If you have two functions in there, you can find out where they're intersecting. This will tell you the derivative at any point. So if you plug in 6, or if you do 6, the derivative at x equals 1. So the slope of the tangent line at x equals 1 is negative 2.82.
Like under calculate, right, there's an integral. Can you use that?
You can find the integral from a certain value to a certain value. So like, for example, the integral from 0 to 2, and it'll calculate it, and it'll even show you that it shades it in like that, and that's the integral from 0 to 2. Yeah. So yeah, the calculators do a lot. So if you're in a calculator section, know your calculator because it can help you do a lot and fast.
Oh my God, I colored it in.
And I believe, by the way, that, like, let's say that you get really good at your calculator and you're able to use it so well that you finish the calculator section early, and you're like, okay, cool, I'm done, because they give you 50 minutes for it and there's only 17 questions. So if you finish them super fast, I believe you're allowed to go back. Maybe that's not true.
To the same section.
To the previous section? It's just that you're not allowed to use a calculator, so I don't know how that would work.
I think, yeah. I'm saying for the free response. We finished. No, I don't know.
I'm trying to remember what order they go in. I know that obviously
I know we did the non-calculator portion first.
non-calculator. So I think maybe here's how it happens. You do the non-calculator portion first, then you do the calculator portion, they let you use your calculator. Then you do the calculator portion of the free response, and then they take your calculator away again and give you the non-calculator portion of the free response. I think that's how it works.
And you can go back to the
And then, yeah, in that last section, you can go back to any of the previous sections. Obviously, you won't have a calculator, though. But I think that's how it works. So, yeah, this calculator does a lot for you. So we'll be practicing those things and using those things. Absolutely, that's what they're here for. The problem is that I don't know if we have enough for everyone who doesn't have a calculator, so we're going to have to figure that out.
Stats class has a lot
Of these ones?
but they like take theirs home, like
Oh, really?
Mr. Lemire like loans them out, yeah. Like the kids take them home.
Well, I don't think the stats, is the stats one on the same day?
No.
So maybe he'll let us use them if we need a few extras. Or I have some too, but they're the old ones, so that's not good. All right, so that was number 3. Let's do number 4, ln of x minus 1 on the interval from 2 to 5. So let's look at ln of x minus 1 on the interval from 2 to 5. So put that in your calculator. Ln x minus 1. And then our window is going to be from 2 to 5. there's two schools of thought on this. One way is doing it the hard way, and the other one is knowing this theorem called the intermediate value theorem, which is exactly what you said, actually. That's the name for it. It's called the intermediate value theorem. If you look it up in your textbook, the intermediate value theorem says that if a function is continuous, which this one is continuous, all polynomial functions are continuous. If a function is continuous, and if it says that, for example, if I have this function that looks like that or whatever, if there's some x value that makes the function equal f of a, and there's some x value that makes the function equal f of b, that means that if you're looking for some y value that's in between f of a and f of b, then its corresponding x value has to be between a and b. So that's called the intermediate value theorem. And so it's exactly what actually Sierra was mentioning. She plugged in all of these to x, and she said, okay, what are they equaling when you plug them in? What is the y values corresponding to those x values? And she noticed that when she got down to C, plugging in 0 and 2, when you plug in 0 into this, g of 0 equals -1, and g of 2 equals, yeah, what does g of 2 equal? 8 plus 14 minus 1, is that right? So 7 plus 14, so 21. And this y value is in between these two values. And since this function is continuous, if that y value is in between these two values, then its corresponding x value must be between 0 and 2 somewhere. And none of the other intervals work like that. None of the other intervals will give you y values that are around 7. All right, so that's called the intermediate value theorem. So that's the way that's doing it. That's the way to do it. That's the shortest way of doing it. The way I did it, just because I was curious if you guys would be able to do it by hand without having to do it this way. The way that I did it, or the way I looked at it, I should say, is I just plugged in 7 to g of x, and I said, what value of x is going to make this function equal that? It was hard to factor. You couldn't factor it. I tried using the quadratic formula. So eventually, when I got down to the quadratic formula, it was 2x squared plus 7x minus 8. And then using the quadratic formula, I eventually got it down to -7 plus or minus the square root of 113 over 4. And obviously, you're not allowed to use a calculator, so you don't know what the square root of 113 is. But it's the square root of 100 is 10, and the square root of 121 is 11, so it's pretty much in between those two. So I said it was 10.5. So I had -7 plus or minus 10.5 over 4. -7 plus 10.5 is 3.5 over 4, which is about equal to like 70.75. 3 over 4 is 0.75. And then I said -10 minus 10.5 is -17.5 over 4, which is a little bit more than 4, so it's about equal to -4.2 or something. And then I tried to figure out which of these intervals had that point in it. Had one of these 2 points in it, I should say. The only one that had one of these 2 points in it was C, because 0.75 is between those two. None of these other ones had -4.2 or -0.75. That's the way I did it. It got awfully close to this one, so you just kind of have to be careful with doing it like that, but that's just another way to doing it. That's another way of doing it if you forgot about the intermediate value theorem. So just keep that in mind. So yeah, make yourself a little note about this one. Intermediate value theorem, IVT. All those little theorems we learn about in like one day and then we just forget about them the next day, they come up in like random questions sometimes. Obviously, like you can see, there's other ways of doing them, but it just takes a lot longer and a lot more thought doing them this way. Yeah. All right, what about this one? Try this one. So if we draw a picture, h of 3 equals 1. H of 7, 3, 4, 5, 6, 7 equals 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's continuous, which means it looks something like that. It can look different, but it looks at least something like that. Which of the following must be true? So nobody said this one was true. H of 5 equals 5. There's nothing to prove that. So definitely that one's not true. So D is out of the question. A lot of you guys, actually all of you guys said that 1 was true because you guys didn't choose B. So you either think that only 1 is true or that 1 and 3 is true. So for 1, there exists a real number P such that H of P equals 5. That's correct because remember that 5, 1, 2, 3, 4, 5 is right here. If it's continuous, there has to be some number P in that interval that equals 5. They said it's in the interval from 1 to 9. You could actually even go more specific than that and say it's in the interval from 3 to 7. The reason they chose 1 to 9 is just to kind of throw you off a little bit, but if it's in 1 to 9, then it's definitely in 3 to 7. So that's why that one's good. So 1 is definitely true, and that's by the intermediate value theorem. The one that we're unsure about if it's true or not, since we had about a half-half split vote, is H has a maximum and a minimum on 3 to 7. It doesn't have a relative max and a relative min, but it is continuous on the closed interval from 3 to 7. So here's your maximum way up here, and here's your minimum way down here. So that one is also true. It does have a max and a min on 3 to 7, and that's by the extreme value theorem that we just talked about a few slides ago. So if it's continuous on a closed interval from A to B, then it's part of the extreme value theorem, which means that it definitely has a maximum and definitely has a minimum on that interval somewhere. Good. Number 3, and then we'll take a break. All right. And you are allowed to use a calculator for number 3, Lahoy, so get out your calculator. All right, if we look at the intermediate value theorem states that if I know what on the closed interval, if I know what f of a is and f of b is, if I'm looking for some value, which is 0.240, if it's between f of a and f of b, then the value of c has to be between that interval. That's how you could prove it. So if I look at f of a, which would be f of negative pi, so if I trace to negative pi is 0.1445. That's definitely less than 0.240, right?
Yes.
Okay. And if I trace to the other side of my interval, so the other side of my interval was x equals pi over 2, or sorry, negative pi over 2. So if I plug in negative pi divided by 2, of course.
That happened to me too, it doesn't let you.
Is it not, I'm trying to figure out why it wouldn't let you. Should be continuous there. Trace. Negative pi divided by 2. Let's try that. Negative pi divided by 2. What? This is so weird. Okay. If that didn't work, I would just use my little cursor and go way over here. Because why not? Alright, all I need to prove is that there's a point over here that's more than 0.240. All of a sudden, I found it. There we go. So definitely way over here is going to be more than 0.240. Over here is less than 0.240. And since this function is continuous and f of a is, and from f of a to f of b, my value that I'm looking at, 0.240, is in between those two. That means that my c value must be somewhere in the interval. So where it says to prove it, that's what they mean. I just proved it by showing that f of a, I found f of a, I found f of b, and the value I'm looking for is between both of those. Now it says to actually find what c value would give you 0.240. Does anybody know how to do that easily?
No. I just did the cursor. I found where it equals.
Where it equaled 0.240?
I got 0.241 where it equals instead of 2.
Okay. Here's where I would do it to find the exact value.
I went to the table set.
You can do the table setting and go backwards, yeah, to enter the y value. So one way you could do it is go to second table. Actually go to second table set, and then for the independent variable, did you do ask for dependent variable, Lahoy?
Yeah, I asked for independent.
And then if you go back to the table, if you enter 0.240,
But yeah, I just wanted to.
mine won't work. I'm not sure. Here's how I would do it. Lahoy did it that way. Did it work for you? Did it give you a value? Okay, it didn't work for Lahoy. Why would you tell me something doesn't work? This guy over here. Okay, here's how I would do it, because I didn't think that would work. I was surprised you got it to work, and I find out you didn't. That's okay. Normally, the calculator doesn't work that way, where you can ask backwards what's a y value, and it won't give you an x value. So here's how I would do it. I would actually go back and graph the value, back in y equals, actually graph the line y equals 0.240. And then if you go back to the graph, it'll actually graph that line for you, and now all you need to do is figure out where these two lines intersect, because that will be the x value where those two lines intersect, and that'll tell you exactly where it equals 0.240.